Hello, this is David D. Hilster. I am a critical thinker, dissident scientist, and I'm here to tell you the truth about science, something your university professors won't tell you, and something a mass media won't tell you. Today is Finity Day, one of my favorite subjects. Of course, I'm not the world's expert in it. Who is? Dr. Glenn Borkert, in my opinion. He's certainly an infinity guru. Trying to get him on his channel to start doing some recordings because he would be really an interesting person. But I'm going to talk to you about infinity. It's really important to a lot of theories out there, and it's really not talked about almost at all in mainstream, which is really bizarre since it's very important to, like I said, the universe and trying to make a model of it. The idea of infinity and what I am speaking about, or finity, infinity is no end. That is, space goes on forever. You go in a straight line, you'll never come back. There are some people, though, who have models, who are looking at models, that in fact, if you go in a straight line, you're going to end up back where you were. Now, I'm not here to dispute why that doesn't happen, but there are people who believe that the universe actually works in circuits. But again, the idea is to understand what finity and infinity is. Finity is the opposite of infinity, which is it's a finite universe with a finite amount of mass. We also talk about the idea of infinity all the way up and all the way down, something I talk about quite a bit. And I often will say turtles all the way up and turtles all the way down. What does that mean? Well, that means that what we see here, we see bigger structures than ourselves. We're standing on the Earth's in our solar system, the solar system is in the galaxy, and the galaxy are in galaxy clusters or whatever. And it would even go above that. You would go beyond, above and beyond that. In fact, there's a book out there called The Universal Cycle Theory by Steve Putz and Dr. Glenn Borkert. They both talk about that and that what may be the superstructure above that. But in infinity, it doesn't stop there. It just keeps going. And also, turtles all the way down. What does that mean? Well, that means there is no ultimate particle. Well, I will talk about that in this talk. But turtles all the way down, what's that mean? Well, it means that you have atomic structure. Under that, you have subatomic structures. Under that, you have subatomic structures, etc., without end. That means everything you look around at, everything is there's smaller and smaller things going on infinitely all the way down. Now that is very uncomfortable. But you have to think about what is uncomfortable about the alternative of not having infinity, especially all the way down. The part that's uncomfortable is that eventually, if you get to an ultimate particle, I've written a paper about this in one of our proceedings, you get to a point where you're going to say, okay, this is an ultimate particle. And this particle cannot be broken down into smaller particles. So what is its density? It is infinite. Why? Because you can't get small enough to see any holes in it, because if it's the last particle, you can't have holes, because if it's got a shape or something, it's going to have parts. So you have this problem with the ultimate particle. If you do say everything is made out of one particle, you've got two basic problems. One, it would have to be infinitely dense. Because just imagine, the way I look at it is a thought experiment. Oh, I hate those, but I'll think of it this way. Here is the particle. Think of it as right here, this ball. Let's look at this. Here's the ultimate particle. Dr. James Maxwell's. This is going to be worth a lot of money someday. Mr. Maxwell, thank you so much. But this is, let's say this is ultimate particle, and you shrink your stuff down smaller and smaller, 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 until you can try to find a hole to get through it. You're not going to, because of its ultimate particle. It's infinitely dense. If there's a hole to it, it's got to have some type of part. That's the one problem. The second problem is that if you have I'm sorry, gave it away. If you have this particle, and it's the ultimate particle in the universe, it has to be magical. Why? Because it has to organize itself into all this infinite variety you see around you. Look at all this stuff. How could it do that? Well, just like particle physics, you just give it arbitrary properties and give them arbitrary values, And then you say, oh, it's got charge, oh, it's got spin, it's got upness, it's got downness, it has color, it has pizzazz, it has personality. Sorry, in my view, can't happen. And because of this, you get something like Dr. Glenn Borkert says, you can have no partless parts. That means you can't have something that doesn't have parts. It's always going to have parts. The good thing about that, and with our particle model, for instance, that my father and I are working on about in having infinity, is we can explain everything just like Borkert explains everything, because everything above it and below it affects what's going on right here. So that means you don't have this problem of magicness, because let's say in our particle model, what we have, if we have a particle going around a nucleus, well, how does it do that? What keeps it in orbit? Well, a cloud of smaller particles on a level below that. Oh, that's good. And those things, that's how what we would call the electron would go around the nucleus. This is how light goes through diffusion and makes the rainbow. This is how magnetic fields are bent around metals, because we have a lower level. We call them G2 particles. And that's a different level. Then we have G3 particles, G4, G5, all the way down. And each particle is made up of smaller parts, smaller atoms. In our model, that's the way it works. That's an example. I'll give you another example. That's not a particle model. Well, it's a mixture of particle model, but I call it an ether model, and that is Dr. Glenn Borkert's ether model, where he calls it A1, A2, A3. And those A's are ether, and ours, it's atoms. But it's the same idea. Infinity all the way down. So when he talks about ether, how does ether 1 stay around and keep together and does its thing and is moved? Well, it's moved by collision, but also in his universe, he has ether at one level, he has ether at a second level, ether at a third level, and so on and so on. Difference is, of course, ether is sort of like air, what air sound is in air, light is in ether. Just a different type of model. I won't discuss which one's better, which one's worse today. But the idea is neither Borkert's model, ether model, nor our model, particle model, will suffer from the problem of ultimate particle. Now there is how do you say, there's two things that are uncomfortable about it. One is that you have to believe and understand that everything you see, everything, this here, some glass cases for my golden glasses. These have atoms under there. There are little pieces inside those subatomic particles, and smaller than that, and smaller and smaller and smaller. That means there's whole universes inside of this. The upside, now that, oh, well, that's terrible. The good side is that there's a place for it in three-dimensional space. When we talk about parallel universes in mainstream or in all these sci-fi things, a parallel universe is a guy right next to me or in the same space doing all kinds of stuff. But it's in a parallel universe. Oh, it's different. It's physical. It's different rules. It's imaginary. It's fantasy. Whereas infinity gives me worlds, and there's probably, well, probably is. There's infinite amounts of beings, intelligent beings in here. Their lifespans are going and coming, and total civilizations and sort of their universes coming and going all the time. But the comfortable part about it is, again, there's a place for everything. They're all here. I can give you the coordinates of those things, and they don't interfere with me. They're part of me. There's civilizations going on, but who knows? I'm giving you this as a visual way to understand the infinity. Again, that's in parallel universes where they somehow are in other dimensions. Shoot me, that's a double barrel. No, that I do not believe. I want you to think about it. You can think about it, but you have to believe in magic. If you don't believe in infinity, you get magic particles. You can believe in parallel universes. I don't believe it. So the good thing is, yes, there's a place for all those little universes all over and above us. We're part of a chair of somebody at a bigger universe level. Anyways, there's another thing that on the other side, which is very uncomfortable, and I'm bouncing around here, but one of the uncomfortable things is you sort of can't ever get to mass. Where is it? Okay, here it is. Here's my golden case. There's the black hole. And anyways, here you have all the atoms inside here. And in there you have subatomic structure. So even though it looks like solid, and I try to throw this cable, it bounces off of it. Why? Because there's mass here and mass here, and they bounce off. But when I really look at it, they're subatomic particles. They're made of atoms. Most of that is space. And the nucleons and electrons, or G1 particles, whatever you want to call them, going around the nucleons, they're also made of parts. So they're mostly space, because in our model, G2 particles go right through nucleons, just like G1 particles go right through the Earth, sometimes captured, etc., etc. What does that all mean? That means you're never really going to find where the two things meet. Now, that is probably more of a philosophical problem than it is a physical problem, but it's one of the uncomfortable parts of the infinity theory. Finity, on the other hand, you don't have that, because if you have infinitely dense objects at the lower level, they are certainly not going to go through each other. So there you go. There's an advantage to your magical particles, which somehow have to organize themselves. So no matter what you pick, finity or infinity, there's things you have to live with and understand. You have to sort of weigh everything. I don't like magic particularly myself. I don't believe that I can just charge is something in the universe that's fundamental. Fields are. Just live with it. No, I want a physicality for everything. So I choose, my father chooses infinity, Borka chooses infinity, lots of people choose infinity, some people choose it all the way up and all the way down. I agree with Borkert. Some people choose it from here on down. Greg Folk, great friend of mine. So that's what infinity is outside the mainstream. And it's not even really talked about in mainstream at all. I hope you enjoyed my talk on infinity. And like I always say, don't take my word for it or anybody else's word for it. On faith, stay critical, stay thinking. I'm Dave D. Hilster, your science therapist, trying to teach you today about finity and infinity. Ciao for now.